Hello, thank you for coming. This is part one of a two-part discussion of Brillo and Weave. The previous talk by Dave, and thank you, Dave, was really an excellent part zero to the talk. And after my part one and part two at 5 p.m., one of my colleagues will be doing another talk about a smart home hackathon that he did with Brillo and Weave. So I hope you're able to attend for, wow, the next 3 hours. It's kind of like the Brillo track. So we're going to talk in part one here, kind of an introduction to Brillo and an introduction to Weave. The Brillo is fairly hastily done in terms of number of slides, and Dave's talk went into a whole lot more detail, so I recommend that to you. We'll do in just a couple of slides what he spent a fair amount of time on. We're going to go into some detail on Weave, talk a bit about how it provisions the system, how the communications work, a little bit about the protocols. Talk a little bit about the security features and the source code structure. Then I'll do a complete gratuitous plug for some of the Intel boards that implement Brillo and Weave. Talk about some next steps that we're doing for some additional add-ons to Brillo that people might be interested in. And then in part two, we're going to go into a lot more detail and show a fair amount of code in part two. So if you're here for the code, it's coming. So Brillo, I'd like to start by kind of setting the stage for what Brillo is versus what Weave is and what also libweave is, or libmicroweave is. Brillo is the operating system. It's not the communications protocol. It's the operating system based in large part on the lower layers of Android operating system. You know, it uses the same kernel. It uses, by and large, the same HALs. The system services have a fair amount of overlap. We're going to actually take a look at how much overlap there is between the components between them. It's really targeted for the embedded space as opposed to the phone and the tablet or the TV space. It's not a graphical GUI like you have in Android. So it's very much a subset of what you have Android. It does require devices with an MPU. So it's for, with an MMU. So it's for the MPU devices, not the MCU devices. libmicroweave is an implementation of Brillo, of the Weave communications protocol for MCU devices. And you know, in the middle there is Weave itself, or libweave, which is part of the Brillo operating system. It's shipped with the Brillo operating system that provides your Weave functionality in daemons and really the whole network connectivity layer that you need to talk to the web, to the cloud from the Brillo operating system. So as I mentioned, Brillo is based on Android. So here's a diagram that everybody has seen of Android. If you have anything to do with Android, you've seen this. This diagram. So first thing we're going to do is we're going to take a hack and slash approach and say, okay, well, what don't we need in an embedded operating system? We don't need the Java applications. We don't include the Google GMS, the Google services layer. We don't include the Java interpreter or the framework at all, no runtime. And we remove a lot of libraries that either Java use or the graphics system uses. Not included in Brillo at this time. We do keep pretty much the whole Linux kernel. You certainly can have a display driver with a frame buffer and you can utilize it. We keep libc, we keep the SSL layer, and a number of other libraries. And to this we add some additional daemons and libraries for Weave and for the bootloader. There's an AB bootloader that we'll talk about a little bit. The metrics and the analytics reporting. Whereas Weave is the communications platform for I/O devices from Google. Weave provides your connectivity between your device, your IoT device, potentially phones, the cloud, other devices, what have you. It provides a good degree of security. It uses SSL and TLS for encryption for the link layer. It uses a number of transports potentially. Right now it's using Wi-Fi and TCP/IP. It is certainly targeted to also allow you to transport via 15.4 BLE. Right now on the GATT protocol is kind of in there, and more is coming, and other protocols. Really, you should be able to provide Weave protocol over whatever transport port that you can that can move the bits. Or you could, in fact, have daemons inside the Brillo operating system to translate between non-Weave devices and perhaps the Weave in the cloud by doing a bit of a protocol proxy for it. The schemas for devices, whether you're what they call white box appliances, washers and dryers, or refrigerators, dishwashers, thermostats, what have you, those schemas are JSON, are really defined in terms of JSON to describe the device capabilities. There's a number of exemplar devices that Google has defined as part of the Weave implementation. You can find those on the documentation website. Google has provided kind of the minimum functionality that you really would expect for a light bulb or other similar device. And as a manufacturer of that device, you can add to it. You do need to provide the functionality, the JSON definition that Google provides as your minimum base, but you can add manufacturer extensions to them. Web apps can be written using Google APIs, and the Google APIs will take your web apps, your commands for your web apps, and send the commands on to your devices into the device queue, and they'll get executed there. We're going to go into a fair amount of detail on how that works in part 2 of the talk. The authentication is done via OAuth 2.0. Google is your AS. And we're also going to talk a fair amount in part 2 about how the OAuth 2.0 can be used from like a curl script or something like that. OAuth 2.0 is pretty confusing until you've worked with it for a while. Weave device schemas, as I mentioned, with the JSON are very important. You really want to have a common level of functionality across devices of whatever class. You wouldn't want to have, as you see here, a toaster, a refrigerator, or a thermostat that doesn't really respond to a common set of commands, because then you wouldn't be able to write web apps to talk to kind of any toaster and expect it to respond in a reasonable way. Therefore, you need to have a schema for each device class. Now, there's many different sources of schemas and companies and organizations, OCF, for instance, that are they're working very heavily in the area of defining schemas. And it's certainly my hope that in terms of schema definition, everybody's going to get together at some point and agree to a common set of base schemas. Because if we don't have that, then no matter what kind of commonality we have with everything else, the consumer's going to lose. Got to have the schemas really well understood and common between them. The command flow for a Weave device looks something like this, and we're going to go into a little bit more detail, I think, on the next slide. For instance, your mobile phone, iOS or Android, can communicate to your Weave device either through local APIs direct, say, via Wi-Fi, and those APIs can either be public unauthenticated, which would allow you to, say, if you have a music player in your living room and you want to cue music to it and you're on the same Wi-Fi link, if your music player allows anybody to in-queue music, then you could connect to it on a local API without even going to the cloud or having cloud connectivity and shoot over the MP3 file to be played on your speakers. Or you could go through the cloud APIs, and generally you would authenticate yourself through Google accounts to the cloud, and the device would also be authenticated with the cloud with Google accounts. And you can use authenticated APIs to in-queue commands, music, what have you, through the cloud, and the cloud will then forward your request to the device. And of course, you don't need to be in the same room between the device and the phone or whatever you're using in order to do that. So the cloud will proxy for you. There are, the administration of the Brillo devices is pretty much all done through the cloud. There's a cloud console right now, and that's really intended for developers. I'm not real sure how that is going to evolve over time, but I think there will be some evolution in there. So end users can take a good view of all of their devices and administer them in a reasonable way. There'll be some changes there, I'm sure. But in terms of the Weave commands that are provided between the cloud and your device, you can do things like view the device status, you can rename devices, you can do a lot with permissions between Google accounts, and Google accounts can be for your friends or it could be for an app. So you can express, hey, I want this other app to be able to have access to in-queue commands for my MP3 player. And as I said, you can send commands to devices with the developer console. You can actually look and see, gee, what are the commands that this device will accept commands for? And it does that by interrogating the JSON file that had been sent by the device to the console. You can say, okay, I want to send this command, and you can fill in the arguments, and it will enqueue it, and it'll be executed on the device. It's really pretty neat, good way to test things. Now, everybody asks this question. Gee, this is a cool operating system. Weave looks pretty cool, but do I have to use Google's cloud? Right? Well, Google's given all this stuff away for free, right? You can change the code, no problem, to use whatever cloud you want, whatever backend you want. But I don't think you're going to get an easy time getting Google to give you the cloud side of the software. As far as I know, they have no plans to do that. I'm certainly not aware of anything. So you could retarget Weave to go to whatever cloud you want. All the code's there. There's no binaries or anything delivered. There's nothing to stop you from doing that. And use a different cloud. I don't think Google's going to help you to do that. So, okay, we're going to walk through what it looks like to register a phone with, say, an Edison or a Minomax or whatever sort of Brillo device that you have. It starts out, you apply power to your device. And there's your connected device. It's flashing. I don't know if that'll show up on the video. Here's your connected device. And it will, once it's powered up and it hasn't ever been provisioned or registered with the cloud, and we use those terms interchangeably, and they are a little bit overloaded. It will beacon by putting itself up as a soft AP, an access point. And the name of it will be Brillo Starter Board, whatever. And it's pretty clear if you take a look at the Wi-Fi networks being available. Oh yeah, here is a Brillo device that's waiting to be provisioned. And it will kind of sit there because there is no cloud connectivity at this point because it doesn't know, it's in AP mode itself, and it doesn't have an uplink. So you then, take out your phone or your tablet or your Chromium browser connected to really anything that has a Wi-Fi, and you search. You use an application. It's either a Chrome app or a phone app, right? And it will look at those Wi-Fis and it'll say, hey, I found these Brillo devices waiting to be provisioned. Oh, I've also found these other Brillo devices of yours, these Weave devices of yours, that are on your account. Do you wish to provision a particular device? You say yes, you go through a pick list and you point to the device and you give it some information. We'll go into a little more detail, I think, on the next slide. And they'll talk a little bit, and it'll ask you what the access point and a PIN number and things like that. And then that connected device, they talk, right? And then the connected device will start talking to the cloud. It's no longer an AP, it's now in station mode, talking to the AP in your home or wherever, to the cloud. And it will be able to get updates for its software from the cloud. It will upload to the cloud the JSON associated with all the commands that are available. It'll give it its status and that sort of thing. And at this point, your mobile device can talk to the cloud, and the cloud will pass the commands on to the connected device. Or if your mobile device happens to be on a Wi-Fi link with the connected device, you could send local commands to it as well. I'd like to take questions at the end. Thank you. I have a lot of slides, and I'm a little worried about the time. So everybody's happy. So a little bit about Brillo security features. So the security features and requirements for a Brillo device are very, very much the same as Android in most respects. They both use Google Verified Boot. They both require a hardware keymaster. However, for Brillo, you don't have to go to 3K and 4K keys. 2K key is fine. That's really important because a 3K and a 4K key takes either a hardware TPM device or a really high-end chip. And with Brillo devices, embedded IoT devices, you don't really want to put in $100 chips in your devices. You want to put in inexpensive chips wherever possible. And by limiting it to 2K keys, you're able to kind of go down a class in terms of the SoCs that you're using. A cryptographic chain of trust is required. So from the time that the hardware is applied to the SoC up until Brillo is fully booted, the operating system can really be guaranteed that some sort of crypto keys have been used at each stage to verify boot being genuine with genuine software and hasn't been tampered with. The file system for your root and your system file system are all checked, and the user file system is encrypted. SE Linux is used very, very thoroughly throughout the system, and when you write applications, you have to add additional SE Linux rules and such to give your apps whatever permission they need. And of course, you should limit root processes anyway. Pretty much the requirements of Android nowadays with the more recent releases. The Weave security features provide for SSL TLS for link level data privacy. So you can expect not only verification of your data, but encryption of your data on all links between yourself, your phone, the cloud, and your device. Within the device, once you get your packets into the Weave daemon from the outside, and Weave daemon will then decrypt them, it will use the binder to pass the data on to other applications. At that point within the device, I don't believe anything is encrypted. But all the communication paths on the outside should be. I did mention earlier that you can share access through Google accounts from your device to your friends or other applications. OAuth 2.0 crypto certificates are used for the initial keys, and Google provides the server. So rather than, as in the last talk, we're going to do a little comparison between Brillo and rsquo, and they have very similar requirements. They come from different worlds, but they're getting to a very similar place. They both have Linux kernels, of course. Userland, Brillo is based on Android with Android makefiles with the Bionic library. Very different than Yocto, which can kind of take standard makefiles and Yocto recipes and uses a bit of a more standard libc. They both have an over-the-air update mechanism. One thing that you'll find about rsquo and OCF for that matter, there isn't a defined cloud service where you can just hook up and go. You need to set up your cloud service in addition. Well, that's good and bad. If you want to set up your own cloud service, you can do that. It's bad because, well, if what you want to do is make a device and just kind of get it out there, it's really kind of nice to have a cloud service, whether it's Google's or somebody else's, just waiting for you to hook up to it. The compatibility in terms of source packages with from rsquo, you get really any open source, Linux-y kind of a package. You can expect it to pretty much just work on rsquo. You may have some challenges doing that with Brillo. The make files all need to be ported to Brillo or Android. You may run into some problems with the Bionic library. It can be annoying, but I think you'll find that a lot of packages that you might want to use have already been ported to Android anyway, so it isn't that big of a deal. On the other hand, if you have an Android source package you just want to use with Brillo, boom, it's just going to work. Whereas with Ostro, you have the complementary problem. IPC mechanisms, binders used pretty much exclusively in Brillo. As was mentioned earlier, dbus had been used, pretty much not used anymore. ASHMEM is used in Brillo just like in Android as well. I don't have it listed there. Ostro will use dbus and Linux IPCs. And they're both open source. Now, Weave versus IoTivity is also a very close parallel on really each level of kind of the layer cakes that can be used to describe the protocols. So in terms of cloud infrastructure, for Weave, Google Cloud Infrastructure, it's there, it works. You just hook into it. All the Google Cloud services that you might already be used to using, they're just going to be there and they're just going to work. Whereas IoTivity, well, you have everything you need to hook up to a cloud, but there isn't a cloud out there waiting for your commands. So you need to solve the cloud problem at the same time you solve your device problem. Cloud infrastructure for IoTivity is all open source, but on the other hand, for Weave, not so much. It's Google's cloud infrastructure, and you really need to work through their APIs, unless you're going to do a lot of work to retarget things. User data privacy are very similar. An interesting thing, though, is for IoTivity, they are trying to get to an end-to-end data privacy, which means that within your box, inside your box, once your packets have landed in your IoT device in IoTivity, if you pass the data off from one process to another, my understanding is they're trying to design to make that encrypted as well, so they can ensure that that doesn't get cause an unexpected leak. It's an interesting requirement. And I don't think the code's there yet, but my understanding is they're moving in that direction. Weave will use a certificate-based authentication from the AS. IoTivity uses another method. IoTivity can self-organize a network. You turn on a bunch of IoTivity devices, and I'm not exactly sure how this works, but they can basically use DHCP internally, find each other, and set themselves up as a network. With Weave, you really need to use a telephone or a Chrome browser or something to bring each of the devices into your account and tell it how to join the network, or in the case of Bluetooth or eventually 15.4, that it needs to be adopted onto your gateway device. The request response protocols, similar in some ways. Weave uses HTTPS and TCP, whereas IoTivity will use more of a binary protocol, COAP, and it can run over TCP or UDP. The IoTivity runs on a wide variety of platforms and different OSs, including Windows. It's not just for Linux, whereas Weave is intended to be multi-platform, multi-OS, but it really isn't realized as that yet. I think that's kind of more of a long-term plan. Certainly with libmicroweave, you could take that code and port it anywhere. So we'll see where that evolves in the future. IoTivity already has some support for gateway to non-native devices. For instance, if you want to talk to a Zigbee device from IoTivity, they already, I'm told, have plugins to do that. That's certainly planned for Weave devices, not there yet. And there's certification programs available for both of them. Okay. Going to get a little bit into the Brillo code structure and comparing it to Android and what the directory layout looks like. So first thing you see when you compare Android versus Weave, rather Brillo, is the huge amount of overlap. So there's just over 500 AOSP projects in the master branch of Android as of a couple weeks ago. Brillo has 190 projects. Of those, the overlap of that 190 is 146 projects. That's huge. Huge commonality between them. The projects unique to Brillo, and I think that number, the math doesn't work out there, but if I say 42 there, even if the math isn't working out, a lot of them are device specific. Let's see, down here, right? So what you're seeing at this stuff at the bottom here is the BSP files for the Edison, for the Minnow, for the Dragon board, and other boards. It takes 1 or 2 repositories per board really to bring a BSP, an additional BSP into Brillo. We also have the common kernel right here that you see. Oops. The common kernel, which is not required for a Brillo device, but it's really nice if you have it. So right now, for instance, the Edison is using a 3.10 kernel, and we're working on bringing that up to the 4.4 level. The Minnow board is at 4.4 level. I'll be talking about the upboard in a few minutes. It'll come out at the 4.4 level as well. And I think the intention, the request from Google is, as much as possible, let's try to use Google's common kernel 4.4, and then when a forklift to go from 4.4 to 4.6, 4.8, whatever occurs, a lot of the work will be done for us. So we, as BSB or SoC vendors, don't have to do that work. We just have to check it out, and Google can just make sure that things work. And that'll be very nice. Means that I won't need to have a big kernel group doing upgrades of kernels all the time. So the rest of the projects, as you see in the top there, there's a generic Brillo project where Google throws different make files and some example code and a lot of the Brillo goodness there. The Gen 2 stuff, I don't think it's being used yet. It will be later, possibly. The peripheral manager is a new component, which we'll talk about in a little bit more detail, I think, in a couple of slides. I think that's in the part 1. The BDK is very important. That's where a lot of the tools are that you use to build products and to download BSPs for whatever board you're using. And there's some common code and some example code and such. But it's pretty straightforward stuff. If you take a look on the left side of the slide where I'm talking about the board support packages, this is what we have there for Intel right now. The vendor BSP Intel isn't actually a Git repository. That is downloaded by the brunch command, which is part of this Platform Tools BDK Git repository. And what it'll do, it'll go out to the web, and it will go to a particular location, usually on GitHub, and find a branch and a SHA-1 for code that needs to be part of the BSP. It'll download it, put it onto your workstation, and put links in your tree so vendor, BSP, whatever you need, have directory links to different pieces of code that you need to build for your board. It's actually pretty slick. And it's easy to add more code to it. Hardware BSP Intel is where we have the definitions for the SoC itself and for all of the HALs. There's a peripherals directory, for instance, there. And under the peripherals, we have like a sensors HAL and our Wi-Fi HAL, et cetera. We'll take a look in a little more detail on that. There'll be a board directory for each board. There's one for Edison, there's one for Minnow, there's one for the Cherry Trail for the upboard from Aeon. And you can have kernels as well under hardware BSP kernel if you're not using the common kernel. I did mention the brunch command. It's very, very handy. It does a lot for you. And when you're making products, as opposed to just taking the BDK, the Brillo Development Kit, or the AOSP Master Branch, and just building and putting it on a board, which you certainly can do. When you're making a product, you'll use the brunch command to create a new directory. It's actually outside of your source tree, and it will put in some symlinks in there to point to the BDK that you had downloaded or that you had used the repo command to suck in. And you could create your project. You can add additional commands to it. It will provide kind of a command proxy to get to fastboot and to ADB and other commands that you might want to do with your device. It's handy. Brunch really is useful. The thing that you use most with it is the download command to get new copies of that vendor BSP directory. So I have mentioned the hardware BSP Intel directory. There's hardware BSP Qualcomm as well for like the Dragon board. So in the Intel directory, you'll find an SoC. Take a look at the middle yellow box there. The SoC directory has, for each of our supported SoCs, we have a directory, one for Bay Trail, which is the SoC being used in Minnow, one for Cherry View, which is the SoC being used in the upboard. We have a common directory there for some tools, and then the Edison directory. And each of those directories will have some make files and some SE Linux files and such. I'm not showing the files here, I'm just showing the directories. It'll have the init.rc files and so forth. The HALs and additional tools are in this peripheral directory. So as you see here, there's an audio, a Bluetooth, a displays. I have an example there where I just kind of thrown in some cool stuff that people might want to use. We can put additional libraries. I'll talk about MRAA and UPM in a moment. The HAL for lights and sensors and Wi-Fi are all here. So for any particular board, you know where to go to find all the BSP pieces. There's actually a document from Google that lays out very clearly for the SoC vendors who are making these BSPs how to do it, where to put things, what the requirements are. That's a good thing. If you take a look at Android, it's a little bit of a mess. If you pull, I'm going to take questions at the end. All right, delving in a little bit deeper, now taking a look at, for instance, device Intel Edison directory, which is the definition for a board as opposed to the BSP. A board is different from a SoC, rather, which is different from a product. Right? They're very, very clear. In this direction, you have the Android board.mk, which is pretty much the same as a standard Android board.mk, but it is also greatly simplified. The structure of it is similar, but since we have an SoC directory, all the SoC-related stuff for the board has been pulled out of there and put in the SoC directory. And what you'll find in there is a few definitions and a lot of macro calls that just kind of suck in the code that you need. And it makes it really easy to create a new board. In the base product directory, there's some scripts that you might add, and a very important weaved.conf file where you define what the model is for your starter board or for your product. If you're doing a product, it would override that weaved.conf file. You can kind of throw whatever you need in under that directory. We don't put a lot of source code in there. We really put control files in there. The source code we try to put in the peripheral directory. We try to put binaries in the vendor BSP directory, and we try to put really just some script files and make files and similar things in here. The gpt.ini is our partition table, for instance. We put it in here on our devices so the user can change the GPT and the partitioning on their device, for instance. Right, a little bit more now on the vendor BSP directory that I mentioned. This is where you put your binaries. This is where you put stuff that gets sucked in from external Git repositories that are not part of AOSP. But you need to do your build. What you're seeing here is basically our firmware, Intel firmware, IFWI, Intel firmware, I don't remember what WI stands for. Firmware for Intel, all right, whatever. For the Edison board, we have similar directory for the Minnow board and the Up board. The the Edison uses U-boot, so we include copies of the U-boot binary. If you want to rebuild your U-boot firmware, you can do that, and that README there has a pointer to the Git project that has the source for the U-boot binaries. So there's no reason you can't rebuild your bootloader. In the peripheral directory there, we have firmware that comes from the outside. For instance, the BCM 43340, which is the Broadcom chip on the Edison is there, as well as the Wi-Fi firmware. So interesting thing about those, we didn't put those firmware files out on the web. They were already published there. All we had to do was point to the Git project that already existed and the branch and the SHA1. So it just made it really easy to throw it out there. And you can put whatever other files you need on there or that the IHV who's building a device for might need. So here's our plug for the devices out there now. Let me just skip up. Yeah, okay. I'm going to talk about the existing and soon-to-be devices, at least from Intel, out there. There are, to be sure, some ARM devices out there. There's a MIPS device, I believe, out there from Imagination. So there's quite a wealth of devices either out or soon to be out. And by out, I mean in the AOSP master branch as opposed to in the latest BDK. It's where you see the latest code. So the Intel Edison kit is really kind of neat. The Edison is that little module kind of in the middle top there. It's a module that has a Merrifield processor, a Wi-Fi chip, a Bluetooth chip, and an eMMC all on board, boom, as one really cool little package. And it fits on an expansion board such as the Arduino expansion board on the top. You see that blank on the bottom left of the top right board. And it just kind of fits in there with the connector, and it provides the processing complex to go with the I/O on the expansion board. And you can hook up a whole bunch of other, really kind of interesting things to it. That's an accelerometer on the top left. That's another accelerometer in the middle there. On the bottom here, that's, I believe, the Grove kit. Is that the SparkFun or the Grove kit? That's the Grove kit, yeah. That's the Grove kit, and this guy right here is a mezzanine board, kind of a hat, that fits on the connectors of the Arduino expansion board, and it provides I2C, A to D, D to A, and GPIO connectors. So it's really nice. You drop that on the Arduino expansion board, and then all of these other little pieces here in that Grove kit have little wires that you just pop right on, and it's so easy to do. You want to get an accelerometer, you just take your accelerometer, put it in one of the I2C slots. You want to talk to a GPIO, no problem. You just take a wire, put it onto one of the GPIO slots, and you're off and running. The libUPM and libMRAA have drivers ready to go for pretty much all of the devices in that kit. The same Edison can be dropped in on these cute little boards. So the Edison is, it's about an inch by an inch and a half, something like that. The SparkFun boards are just slightly larger. And they're basically, I/O boards, and you mix and match what you want. There's an I2C board, there's a GPIO board, there's a little board with a battery on it, there's serial boards, there's a little display board. Lots of different things that you can just take and just kind of pop on there, and you make a little stack of boards, and the same software for Brillo just comes up and runs on these. The Minnow board Turbo being the current latest one, also has Brillo. This one's in AOSP, it's not in the BDK. And it also has mezzanine boards. You see them here. They either go on the high-speed or the low-speed connector. And they can add lots of different functionality to your Minnow board. The Minnow board doesn't have an eMMC. You boot the Minnow board from a SD card. Here's the up-and-coming upboard from Aeon. This was a Kickstarter project that they did. It's a very cool board. Love this board. So it's kind of like the Minnow, but it adds in a lot of stuff that I wish the Minnow had. It has USB on the go. It has an eMMC. It has CSI and DSI ports. Very, very nice. So this is a fun board to work with. And they're going to be out soon. The early developer boards have been out for a while. They're just kind of finishing up their debugging process, and these will be shipping from them soon. And we'll be providing, as soon as they release the kernel drivers for the upboard, we'll be providing support in AOSP for it as well. Okay, back to Brillo and Weave. So Weave plus Brillo provides the upstream automatically. Actually, there's a switch that you use to turn on the reporting of analytics to the Google Cloud, but it provides all the framework that you need to provide board statusing information, and the Google Cloud will keep track of a lot of really cool information about your boards in aggregate. Clearly, for privacy reasons, you don't want to be able to see from the developer's console users' private data about any particular installed board, but you do want to look at the aggregation of information so you can understand what's failing, where there's crashes, where devices are rebooting a lot, what your installed base looks like, and that sort of thing. So I'm going to go through a number of the available graphs in the analytics. This one here just is showing registrations over time for boards of a particular model. So when you go through, and in part 2, we're going to go through in some detail what it looks like to create a new board model. When you register a new model with the cloud and somebody takes one and turns it on and then associates it with their Google Cloud and all that sort of thing, there's a string, I think it's a 6-digit alpha or alphanumeric string that is shared with the cloud. And the registrations for that device are tallied by the cloud, and you can see as you get more devices registered or devices drop out, that sort of thing. So there's just small numbers on all of these because this was just for my private cloud. This is which devices are online that are registered, and here you're seeing in blue the onlines versus the total registered in yellow. And product versions. So over time, as you use the OTA mechanism to publish updates for your device, these updates will get pushed out to the physical devices, which check in every now and then, certainly when they have web connectivity. And the console will track all the versions that have been released and the number of devices using each version. So if you see that some devices are not getting updated, they're using old versions, you'll be aware of it. It's useful for tracking issues in the field. You can take a look at the number of Weave commands being sent to your devices on a per time basis and what those commands are. So if I send a command to turn on an LED on one of my starter boards, or I want to enable metrics or something like that, the console will aggregate all that information and make it available to the developer. There's also a lot of logging information. I'm not going to go through all of these screens, but there's, as you see here, crash reporting, CPU usage, use times, page faults, bulk storage use, memory use. So you can drill in, again, in aggregate to see what your devices are doing in the field. And if you find that the storage activity, you're doing a lot of I/O activity on your devices and you don't know why, you might want to drill into that in terms of debugging. So it's pretty cool, very useful. Next steps. So these are not necessarily Google projects. They're certainly not necessarily committed. They're things that we're looking at or that we think need to be done or we think maybe Google is looking at. So Java is likely to be pulled in and not hard to pull in. We've done some investigation working on that already. Since it's in the Android tree anyway, turning on Java is a pretty easy thing to do. The question for Java really is, well, how much of the Java do you really want to pull in? Do you want to pull in The Java runtime, certainly, right? You could go to the Open Java if you want, but the Google Java, the Android Java is just there. So might as well just use that. But then how much of the framework do you want? Do you want to have just enough of the framework to be able to do some JNI code and write some daemons? Do you want to have a little more of the framework so you can utilize the crypto, maybe a little more of the framework so you can talk to the display? Or do you want to have a whole lot of the framework so you can, I don't know, possibly do some of the GMS activity once Google makes that available for Brillo? So the question is, how far you dial it up and down. Camera support is important. I think camera in IoT is just gonna be very, very useful for everything from baby monitors to DSS. Display, I don't think you're gonna need display quite as much, with quite as much performance and interactivity as you have on something like an Android. Otherwise, go ahead and use Android. But you're gonna need some display activity. That might be control panels, where you touch buttons to start your dishwasher. It might be putting ads up there to reorder soap, for your washing machine, what have you. So simple kind of web interactivity is where, at least in my mind, the display is going to be for Brillo. Although Surface Flinger can be used, there are alternatives, such as I mentioned at the bottom there, nw.js is kind of an interesting way to consider doing your display. Bluetooth is kind of there now using GAT. There'll be further work on Bluetooth to be sure. Voice command and control is going to be really important in this area, as we've seen with the Echo. Connectivity to other kinds of radios as well. At Intel, we're, in addition, exploring JavaScript, Node.js. In fact, our JavaScript and Node.js work is essentially complete, and we've upstreamed the Node.js work for Brillo. So at some point, we'll be publishing exactly how to use it. And nw.js, which is, as I mentioned, for displays, it's really cool. It's kind of Node.js plus the Chromium browser to just paint on the display. So in part 2, I'm going to go through code. It's really almost entirely going through Google's Code Labs, going through code, showing how pieces work together, and kind of a walkthrough of the hardware access layer as well, how the different pieces interact. So I hope you'll stay for it. And after part 2, there's another talk by one of my colleagues about a smart home, actually taking all these concepts together and how he implemented a Brillo system to kind of control kind of a dollhouse. So we have just a few minutes, I think, for questions. We'll take however many we can. Yes?
How the OTA updates will work? So you said that...
There's a microphone. Go ahead and wait for the mic.
So you said that the Brillo API can be decoupled from the Google Cloud, right?
Can be what?
Can be decoupled from the Google Cloud. The Brillo...
Oh yeah, instead of the cloud? Well, I'm suggesting that perhaps it can. After all, you have the whole source code. I have not looked at how to do that.
Okay. So how about the OTA updates? The OTA, Google, when administered the device updates? Google...
Yeah, so you'd have to work that out too, because right now, your Brillo system will use the Weave commands to talk to the cloud, and when there's an OTA update, you'll be notified from the cloud that there's an OTA. If you're going to pull yourself out of Google's cloud, the question is, do you leave enough Weave in there to continue to use OTA, or do you invent your own OTA mechanism as well?
Got it.
So
the OTA updates are done with the bootloader?
Yeah, Google pushes your OTAs for you, and it makes it really, really easy to do.
Awesome.
I've done them, and it was really no sweat to send OTAs out.
Got it. So even for development, you can play with that, is it?
Yeah, you can do it from the development console.
Awesome. Thank you.
Sure. Yes. Thank you for being patient. Please shout.
So this access to Google Cloud for Brillo, is this available to everybody, or do you need to be in that special program?
It's by invitation only right now. If you go to the cloud, you'll get a I'd like to be invited link. You click on it, you put down your information. If If you don't get an answer on that, you might send me a note. Maybe I can get you some help getting an invite. No
Okay.
guarantees, though. It will go general availability without invitations at some point soon. I don't have a date for that.
Okay, thank you. And the Edison, I have Intel Edison, but it runs the Poki Linux.
It has what in it?
Poki Linux?
Oh, that's fine. We as part of your setup procedure for Edison for Brillo, you overwrite the BIOS and all the code on there and put Brillo in instead. So you would lose Poki.
That's fine, but I can bash.
Absolutely.
Okay, thanks.
Yeah.
You mentioned libmra and libupm, so that works natively already on
Yep.
the boards?
I'll talk to them quite a bit on part 2 of the talk.
Oh, okay. Are there any licensing issues there? Are there any licensing issues?
No, the licenses are just fine.
Okay. So what's the license for Brillo?
I'm sorry?
What's the license for Brillo?
Well, there's a number of different licenses. Most of it is APL. There's a little BSD in there. There's a couple parts where there's a little bit of GPL, but it's we've tried not to add any actual GPL code in our BSP. So it's all self-consistent, and APL is by and large your preferred license. Apache. Was there a question in back? Oh, it looks like I'm done. So thank you very much.